Hello AP Chemistry and welcome to weak acids. So, this is what we talked about at the very beginning of chapter 16, right? Where our acids undergo a hydrolysis reaction with water to produce hydronium and the conjugate base, right? Now, when we're talking about any weak acid, right, then this becomes really significant, right? So we talked about before, if we have a strong acid, and this is 0.1 molar, we could assume that this was going to be 0.1 molar. But if we have a weak acid, is it a strong electrolyte? No, it's not a strong electrolyte, right? Meaning, does all 0.1 molar acid dissociate? No, some random amount dissociates based on, ding ding ding, Ka values, right? Which means that here, our Ka expression actually becomes really important, right? Because we have this, and we have this, right? And now this becomes important, right? So this number is going to be what kind of a number? Right. It's going to be less than 1, right? Because we know that this is not going to dissociate completely, okay? But the same principle still applies, right? The bigger my Ka value, the stronger my acid, right? The bigger my Ka value, the stronger my acid. So something that has a Ka value of 10 to the negative 4 is a stronger acid than something that has a Ka value of 10 to the negative 7. Yes? Right? Bigger means more dissociation, meaning stronger acid, right? Because that means if we say that there's more dissociation, we say that we're really saying it produces more of the hydronium ion, right? Which goes back to a lot of the same language you used when we talked about the KSP expression, right? Where when we talked about how going forward meant making ions, right? Going backwards meant, in that case, making precipitate, right? Here, going forward again means making ions, right? Which in this case means hydronium ion, which means increasing pH, right? Okay, so anyway, so this is all going to be tied together by my Ka value, which is a constant based on temperature, yes? Meaning that that constant is going to influence all these values. Okay, now, next up, moving along to some different kinds of weak acids, right? So you've memorized all your strong acids, and basically if it's not a strong acid, it falls into the realm of weak acids, right? So some of these should be familiar, right? So chlorous acid is a weak acid. And don't forget, this is what we talked about back in chapter 4, right? The hydrogen is always attached to an oxygen, despite how we write it in the formula, right? It's always attached to an oxygen. So if we look here, right, that hydrogen attached to an oxygen. Hydrofluoric acid is one of the only weak hydrohalides acids, right? Nitrous acid attached here, right? And again, we know that nitric acid is a strong acid, chloric acid is a strong acid, and these are their weak acid counterparts. Now, here we have these two, which look strikingly similar, right? We have this COOH group, right? And again, in organic formulas, we often write things to represent their structures, right? It's written this way because it represents COOH, right? COOH, right? And this is known as a carboxylic acid group, right? Or carboxyl group, right? And it's always going to be recognized as COOH, which means that every time you see this as part of a chemical formula, you should understand that it looks like this. And by extension, that proton is ionizable. That proton is losable, meaning that this can be deprotonated. It could also be called the acidic proton, okay? So that acidic proton can be removed or lost, forming the deprotonated conjugate base. Yes? All right. And then likewise here for hypochlorous, right, again, a derivation of chloric, right? Hydrocyanic, right, and phenol. So anyway, and you'll see here if we look at our K values, right, again, as Ka increases, my acid gets less and less acidic. Okay? All right. Moving along, let's do a practice exercise. So the Ka for niacin is this, and again we have this COOH, which means that the ionizable or acidic proton is this one, right? And again, don't forget, right, there are assumed hydrogens at all those places. This is the only ionizable one, right? Likewise here, right, there are these other protons, right? Those are not acidic protons. Only this one is our acidic proton. Okay, anyway, going back here. What is the pH of a 0.1 molar solution of niacin? So what's a good place to start? Right, our reaction, right? So we're going to take this plus water, equilibrium arrows because it's a weak acid, because niacin Not on our list of strong acids, right? Which means that we're going to form some of this, and we're also going to form some of, we're going to form some of its conjugate base, okay? Now, in terms of my concentrations, right, I know that I originally or initially start with 0.01 molar niacin, right? 0.01 molar, doesn't matter, and I have none of those, right? Which means that if I think about my changes, right, I'm going to lose one of these because it's only one ionizable proton. I'm going to gain and gain, which means that I'm going to have 0.01 minus x, x, and x, right? Which means that then we're just going to set this all up, right? So I know that my Ka is going to be x times x over 0.01 minus x, and all of this is going to equal 1.5 times 10 to the negative fifth. Here is where in the sample, the accompanying sample problem in your textbook, right, it talks about how, because we would have to solve this with a quadratic, we could assume that this minus x component is 0, and that assumption is usually safe as long as my Ka value is 10 to the negative fifth or smaller, right? Now, that's bearing in mind that not everybody has access to the kind of calculators that you guys are all actually required to have, right? Your guys' calculators have the solve function, which means that anytime you have this, on the free response section, you just work it out, right? You say solve function on calculator and write down what your x option is, right? There's no reason for you to assume, right, that this is negligible, right? Now, if you're asked to discuss that as an option, like, can we assume that x is negligible? Well, you can assume that x is negligible if x is less than 5% of your original value, right? Because when we say that it's less than 5% of my original value, we're saying that it's way out here in terms of decimal places, which means it has no bearing on this in terms of significant figures, okay? So anyway, that assumption is there, bearing in mind that some people may have to work this out using the quadratic equation, blah, blah, blah. You guys don't have that problem, so we're not going to do that, right? Now, if we were on the multiple choice section of the exam, okay, if we're on the multiple choice section of the exam here, yes, we would consider x negligible, and we would solve this really quickly and simply. Yeah, does that make sense? All right. So anyway, so we would solve for x, right, and x would go over here, and then if we want to know the pH, right, x is equal to this. So then the last step would be negative log of that concentration. Make sense? All right. Thank you for listening. Be good, and I will see you soon. Bye.